Part of the power of mathematics is predicting the future. So I invite you, as I did my students at St. Mary's College of Maryland, to do some virus prediction. How many coronavirus cases will we see in the future, and what can we do? In mid-March, many of my students thought the world was overreacting, that COVID-19, the disease caused by the virus, was overblown. Doing the math themselves changed their minds. While those young, healthy students are less likely to die from this epidemic, their actions, and yours, can help prevent many, many deaths. That's not hyperbole, those are the facts. The mathematics of epidemics makes that crystal clear. To see why, let's start with a simple model of change and move toward more complicated ones. The simplest change is linear, just adding the same number every day. If some hypothetical illness started with just 2 cases and grew by 100 every day, the math to predict the number infected I during this time is just 2 plus 100t. Graphically, it's a straight line with constant slope. The rise over run is always 100 cases per day. Beyond looking at the number of cases, we also want to look at how that number changes. In a linear case, the rate of change, written I prime, is constant. Here it's 100 infections per day. If we keep it linear but change the rate of infection, all we're doing is changing the slope of that line. Maybe instead of 100 per day, it's 150. Steeper, but still a straight line. But the coronavirus outbreak is definitely not linear. Early numbers were 15, 16, then 24, 53. It wasn't growing at the same rate each day. Instead, the rate of change kept getting faster and faster. Any outbreak like that means that the number of people infected already influences the number who get infected next. This isn't linear, it's exponential growth. Let's look at what happens if the number of cases doubles each day. Start with 2 cases, just like before, but instead of adding 100, watch what happens when we start doubling. At first, the exponential numbers are so small you can't even see them. Throughout the first week, the linear model is higher. Shortly after a week passes, the numbers in our exponential model pass those in the linear model. And now the feedback loop in the exponential model is really starting to flex its muscle. Every day the linear model adds just 100 infections, but the exponential one's rate keeps increasing, adding about 1,000, then 2,000, then 4,000. By day 20, the linear model straggles along with about 2,000 cases, while the exponential model soars to over 1 million. This explosive exponential growth is hard to fully grasp. We tend to think that any rate of growth we've already seen is what we'll continue to see. We have an unconscious tendency to believe that change will continue at the same rate. We have a bias toward linear thinking. But when something is exponential, it's the doubling time that's constant. So if you want to follow the change over time on an exponential graph, you keep zooming out. You have to rescale to see it all. In order for a single graph to visualize this multiplying rate of change, it's helpful to rescale using powers of 10. So now we're multiplying from 1 to 10 to 100 to 1,000 and so on. A logarithmic scale. Graph our 2 models on a logarithmic scale, and the linear function bends downward. Now it's the exponential function that becomes a nice straight line. My students took the data, plotted the number of COVID cases in the US, and saw an exponential graph. They switched to a log scale and saw roughly a straight line. The numbers were doubling about every 2.5 days. They dutifully did some calculations, predict the number out a week or 2. But the last question was the one I desperately wanted to know the answer to. I hadn't even had the time to work it out for myself. How long before every available hospital bed in the US was filled? We found the data saying that about 1 in 10 cases required hospitalization, and the US had roughly 400,000 empty beds. We plugged in the numbers, and the answer stunned us all. If the coronavirus kept spreading at the same exponential rate, we had just about a month from mid-March before all the hospital beds in the US would be full. 1 month. And in some places, the beds would actually fill up sooner. Our estimate assumed that the first waves of sick people were in exactly the right places to use all the empty beds. Calculating how quickly the number of serious cases would exceed the total capacity of hospital beds was a huge wake-up call for us all. If everyone went along with business as usual, we would go from a few hundred isolated cases to an overwhelmed healthcare system. When my students did their prediction, outbreaks had already started around the world. but not all at the same time. And because of those delays, it was easy to misinterpret the numbers. At one point, Italy had about 8 times as many cases as the US. That feels like a lot, something like 4,000 in the US, but 32,000 in Italy. But since the numbers were doubling every 2.5 days, here's what that meant. The US numbers would double in 2.5 days to about 8,000. 2.5 days later, they'd hit 16,000, and reach Italy's old mark of 32,000 2.5 days after that. What felt like a huge gap was actually just 1 week. To compensate for the different start dates, we can shift graphs over in different countries to show when different outbreaks started. Then we can compare how different countries handle the outbreak. On a log scale, we just have to look at the different slopes. Looking at the website Our World in Data, you can follow how the pandemic takes a different trajectory in different places. Starting each graph when a country hit 100 cases, the first one had doubling times of less than 2 days. Other countries learned from those lessons and did better. Singapore and Japan kept to a doubling time near 10 days, buying time for their hospitals. Eventually, China and South Korea also found ways to fight back. China got out of its exponential line by locking down large populations, including the 11 million people in Wuhan. South Korea implemented a massive testing regime to identify and isolate cases quickly. The US got a late start. As of March 26th, the doubling rate of confirmed cases in the US had slowed from 2.5 days to just about every 3 days, still very fast. How much does the exponential rate, or doubling time, need to change to make a big difference? When we look at the log graph, it might not seem like there's much difference between doubling every 2.5 days and doubling every 3 days. But remember, that's on a log scale. If we switch back to a linear scale, we see more dramatically what a huge difference it makes. If a country makes this change at the beginning of their outbreak, lengthening the doubling time from 2.5 to 3 days, they'd cut the number of infected about 75% during that first month. Over 40 days, that gap widens to 85%. Early action to reduce the infection rate pays huge dividends. Conversely, this also means there's a huge price to pay for any lack of early aggressive action. The more you act early, the more lives you save. These exponential models track outbreaks very well, but even bad things must eventually come to an end. If you start from just one infected person and double 33 times, it takes you past 8 billion, the number of people on Earth. Such models never know when to stop. So any simple exponential model eventually becomes unrealistic, no matter how long the doubling time. These models ignore the fact that as more people get infected, fewer are left to infect. So let's look at a more realistic model that tracks not just the number infected, but also the number who remain susceptible and the number already removed from being infected or susceptible. This model dates back to 1927 when it was published by 2 scientists in Scotland, physician Anderson McKendrick and a blind biochemist named William Kermack. Because their model tracks the number of susceptible, infected, and removed, it's called the SIR model. The proportion of the population that's susceptible, S, at first includes everyone. The susceptible gradually become infected, I. As the infected recover, they flow to the group removed from infection, that's R. How quickly people get infected depends on the rate of contact, C, which is absolutely crucial. And how quickly someone is removed from the infected status is expressed with another constant, which we can optimistically refer as to the rate of healing, or H. I say optimistically because for understanding how the virus spreads, it doesn't make a mathematical difference whether someone recovers or ends up dying. For epidemiologists tracking an infection, either way, those people won't be passing along the infection anymore. So deaths are actually included here, too. Both the recovered and the deceased are included in the removed category. To predict how a pandemic will play out, we look at how the rates of change of these three are related. First, let's look ahead to people removed from infection, whether by recovery or death. And let's think about how that overall proportion changes over time. Assuming nobody gets reinfected, the proportion who removed is always increasing. The total number and the proportion of people recovered or struck down is increasing all the time. So this rate of change is equal to the infected proportion times the constant expressing how quickly people heal. Meanwhile, at the front end, the proportion of those susceptible is always going down. Each time anyone gets infected, the remaining susceptible group shrinks, so that the change in the proportion susceptible is negative. This rate of change is equal to the susceptible proportion times the proportion already infected times the contact rate. This contact rate will be key, in some sense the most important part. The middle group are the proportion infected, but in this model, the change in infected has two parts. We add the susceptible people who are getting infected, but then we subtract the infected people who recover, who are removed from the infection because they don't survive. So, which flow is bigger? The pandemic is getting worse if the flow of people getting infected is higher than the flow of those recovering. That would mean the infected group was growing, and we'd see that if the contact rate C is large enough. Since it looks like everyone starts out susceptible, and a vaccine is perhaps a year away, the initial value for susceptible is 1. That leaves us with a ratio of the contact rate C over the rate of people healing H, or otherwise ceasing to be among the infected. This ratio is so important it gets its own name. It's the base reproduction number, R0 or R0. This one ratio helps explain a lot about an outbreak, and here's another way to look at it. The reproduction number R0 tells us on average how many additional people each infected person will infect through the duration of their infection. Think of it this way. If the infected people have an average number that is more than 1, they are collectively throwing more gasoline on the fire of exponential growth. Remember, if you infect 2 people and then those 2 people infect 2 more and so on, then we're back to exponential growth. We've seen how bad that gets. And exponential growth like that happens anytime the average reproduction number is even slightly more than 1, like 1.5 or even 1.1. On the other hand, if we can make R0 even a little less than 1, then infected people recover faster than they infect susceptible people, and the outbreak isn't as bad. Unfortunately, assuming normal human activity, the estimates for the coronavirus reproduction number are between 2 and 3. For a pathogen, that's huge. It's much worse than seasonal flu, and it's even higher than the 1918 Spanish flu pandemic. That's why we've been seeing this new coronavirus spread so quickly. So what do? We don't have a lot of control over H, the rate people are healing from the virus or passing on. Having enough hospital beds and respirators and good medical care can definitely make a critical difference for survival in the most serious cases, but without better treatments, the rate of escape from the virus often remains substantially beyond our control. But here's the good news. The contact rate C is something we really do control. Collectively, we can control how likely it is that the virus is spread. The model predicts how the infection will play out. If the contact rate C is large, then the reproduction number R0 is large, and the proportion infected overwhelms our medical systems before eventually dying down. But if everyone washes their hands with soap for at least 20 seconds, the contact rate C goes down a little bit and the infected curve flattens a little. If everyone avoids touching their face, I know how hard it is to stop, but it keeps the virus from getting into our mucous membranes. Then the contact rate C goes down a little more and the curve flattens a little bit more. And most importantly, and probably the hardest, if we isolate ourselves, we can drop the contact rate really low. That's what social distancing is about. That's what shelter-in-place orders are about. Shrink the rate of contact as small as possible, and we can flatten the curve and reduce the burden on our doctors, nurses, and hospitals. This is the cornerstone of what eventually worked in Wuhan in South Korea, and what can work anywhere people make a sustained collective effort reducing the contact rate. Building new hospitals or providing mass testing may help a country catch up from behind, but shrinking the contact rate is uniquely powerful everywhere. The mathematics proves it. And this SIR model is only the start of what epidemiologists know. Even more accurate models include more groups like the exposed between susceptible and recovered. That's important because the coronavirus appears to have a long period before the signs of infection appear. And these models now run on computers as part of large-scale simulations, including agent-based models which track and predict the stages of a pandemic more accurately than ever before. All of that work points in the same direction. If we, and it does take all of us, act quickly, the sooner the better, we can minimize the impacts and save lives. And if you know anyone who isn't taking this coronavirus seriously and you think this video could help, please share. Thanks, and stay safe.